Hello everyone, I welcome all of you to Physics for All by Shilpy Bhullar. As you all know, we are doing video lecture series based on vector analysis. So today we are going to discuss the last topic, which is Green's theorem from the main topic of vector analysis. Green's theorem is also an important theorem as it is a special case of Stokes theorem. In the previous video, we discussed Stokes theorem. So how is this Green's theorem different from Stokes theorem? Well, this is a special two-dimensional case of Stokes theorem, and it is also known as Green's theorem in the plane. So if the word plane comes in, that simply suggests that we are talking of a particular plane which is two-dimensional. When we were discussing curl of a vector function in terms of Cartesian coordinates, there we solved it for particular xy plane. We did the complete solution for xy plane, and then we said that the similar pattern goes for the yz as well as the zx plane. And then we summed all the integrals that we solved for the individual planes to get the final answer. There also, we started with a particular plane. We solved for xy plane, then we wrote down for yz plane, and then for the zx plane. And then we added all those up. But in case of Green's theorem, it's special case of Stokes theorem, and it talks only about a particular plane. That's why we also call it Green's theorem in the plane. What does it do? It actually gives the relationship between a line integral around a simple closed curve C. As you can see in the figure, again there is a closed curve which is C, and being a closed curve, it is enclosing some surface S. So it gives the relationship between line integral around that closed curve C in a plane and a double integral over the plane region S, which is being bounded by the curve C. You can see here that this curve is a closed one. Being a closed curve, it is enclosing surface S. And for a curve, since it just represents one dimension, we talk of line integral, and the surface S, since this represents two dimension, we talk of surface integral, right? So for this surface, we have to find the double integral. It is similar to Stokes theorem because Stokes theorem also relates line integral around the curve with the surface integral over the surface which has been enclosed by the curve. So Green's theorem is almost identical to Stokes theorem, but only it talks about a plane. So it stays in the plane. We don't stretch it to the three dimension. In case of Stokes theorem, or you can say when we find curl in terms of Cartesian coordinate, basically we found for a particular plane, we have three planes if we talk of the three dimensions. So we talk of three planes, we find the values in all the three planes, and then we added them up to get the final answer. So that gives us the value of vector function over that region of the space, and space is three-dimensional. And Stokes theorem also utilizes that feature. Directly we use that feature and we directly pick del cross A, which includes the curl around all the three dimensions. But here we will stick ourselves to two dimension and we won't talk of the third one. So we will only talk of a particular plane. And that is the reason it is known as Green's theorem in the plane. So let's start. One more peculiar feature of this Green's theorem is that it involves two functions. Usually whenever we have talked of divergence or curl or Gauss divergence theorem or Stokes theorem, we have considered a particular vector function. We used to say that A is our vector function and we used to solve over that. But this Green's theorem allows us to have two functions, right? So here the statement says if S is the closed region in the xy plane, you can see the figure. We have made a curve which encloses the surface. Surface is denoted by S. XY plane, well, this is the most convenient plane because since the beginning, even in mathematics, when we used to study coordinate systems, we always talk of XY axis. So this is the basic one and the most convenient to use, and that's why we often talk of XY plane in general, and then we just stretch our derivation to YZ and ZX. We are not that much comfortable with YZ and ZX planes, but still you can use them. It's up to you. So that's the reason that we, just for our convenience, we pick XY plane. Mostly everywhere you would find this. So if S is the closed region in the XY plane bounded by a closed curve C, as you can see, the C is the closed curve which is defining the region. And if MXY and NXY are continuous functions, now these are the two functions MXY and NXY. That means M and N both depend on X and Y. So we have not shown any dependence on z-axis. So that's the reason that we are talking about the plane. We are only talking of the plane, and we are saying that whatever functions we have considered, they depend only on those two dimensions. So here M depends on x and y variable, and N also depends on x and y variable. And these are continuous functions. So if they are continuous function, then definitely it would be easier for us to find the integral over these, and they are having continuous partial derivatives in S. So that means they are differentiable and we can actually find the derivatives. So then they are saying, so it involves both. It's some statement part and there is that mathematical portion as well, that if that's the reason and if that's the case and we are talking of only a particular plane, then this is the relation. See, m dx plus n dy integrated over the closed curve C is equals to the partial derivative of n with respect to x minus partial derivative of m with respect to y, and that is being integrated over the surface. So since we are talking of xy plane, so we would be having dx and dy for the double integral, right? So this theorem is a combination. Whenever we did Gauss divergence theorem, we had a complete statement and then we used to write it mathematically. Even in Stokes theorem, we had a particular statement which had a meaning and then we used to write it mathematically. But this Green's theorem has a statement and this mathematical expression combined as its definition or statement. So you can see that it is just showing that if we are talking of xy plane and there is a curve which is binding surface S and you have two functions, two continuous functions depending on the coordinates of that plane. So if you are talking of xy plane, then the two functions should be depending on x and y. So in that case, this is the relation. So that means those functions, if integrated over the curve, their value would be equal to the partial derivative of those functions integrated over the surface. Okay, so let's see how does the proof go. For the proof, we will consider again a vector field A because that's the simplest one. As we have to use curl, since this Green's theorem is a special case of Stokes theorem and Stokes theorem involves curl, the curl of a vector function, we only know how to find curl of a particular, of just one vector function. This is what we know. So we are going to use that formula to actually find what would be the value if there are two continuous vector functions. And let's see, it's kind of tricky the way we have used the vector field A and these m and x, mxy and nxy continuous functions in our proof. So if A is the vector field, then we know that according to Stokes theorem, we would be having this A dot dr integrated over the closed curve C equals to the normal component of curl of this vector function integrated over the surface. As you know that we have plotted the curve in xy plane, And when we talk of surface or the plane, you know now that unit vector is always associated with that. Whenever we have an area, we always consider n cap, the unit vector, which points in the direction perpendicular to that surface. So here again, we have drawn a curve C, which is enclosing surface S. So that surface is in xy plane. In fact, the curve C is also being drawn in the xy plane. So we have to consider a unit vector n cap, which will point in the z direction. If the curve is in xy plane, so that means the surface is in xy plane. So n cap will point in the perpendicular direction, and that is the z direction. So if that's the case, that means our n cap is basically k cap. As vector A will also depend only on x and y, because we are talking of only xy plane, and there is no reference of the z direction at all. So we can say that this vector function A is simply depending on x and y components or x and y direction. And that's why for vector A we have written ax I cap plus ay j cap. Because remember, this theorem that we are doing is Green's theorem in the plane. It has nothing to do with space or 3 dimension. It will only talk of 2 dimension. So the vector would also be expressed in 2 directions. So ax I cap plus ay j cap, and the small displacement that we consider for this a dot dr. So dr again would be dx I cap plus dy j cap. Now see, this is the trick here. The theorem talks of two continuous functions. You can see mxy and nxy are continuous functions over that region, over that space that we have considered, or here we can say over the surface S, and both are depending on x and y. But we know how to find curl of a particular vector function. We have started with a single vector field A, and now we are saying that this vector A is having only 2 components, since we are talking of the plane. Now see, what we have done here is that let m and n be the x and y component. Here we have written, this is the general expression, that vector A is ax I cap plus ay j cap. But now we are referring that let this ax be m and that ay be n. Let m and n are the x and y component of the vector field. So if that's the case, we can write vector A as A is what? This is ax I cap plus ay j cap. But now since we are saying that m is the x component and n is the y component, so this becomes mi cap plus nj cap. So this implies if we have to find a dot dr, in that case we can have the dot product of this mi cap plus nj cap with this dx I cap plus dy j cap. Now you know how does the dot product act. I cap only interacts with I cap and j cap will only interact with j cap. So we are left with m dx plus n dy. And this is the expression you can see which we are obtaining here in the statement. See, you can see this left hand side of the equation. This includes m dx plus n dy, and here we have this expression. Let's mark this as equation 1 and this expression as equation 2. Now using equation 2, we can rewrite this equation 1 as, instead of a dot dr, now we know the expression that we have is m dx plus n dy. So our equation 1 can be written as this m dx plus n dy, okay, and this is the line integral. Now I have removed this close, that circle that we used to write. Now we are not writing it. Why? Because now we don't know whether the curve that we are talking of or the boundary that we are talking of, whether it is closed or not. Though we know that the curve is closed and we can still use it, there is not much of difference. And you are not seeing any dr. Well, even if there is no problem if we write down this circle, if we make this circle. So it's totally up to you, because ultimately still we are talking of the curve C. But now we are not having any dr on anything, but that job is being done by dx and dy. See, when we are having single integral, that means line integral, we need just one variable to integrate the expression, whatever variable we have. So you can see here the m, we will integrate m with respect to x. So we have that one variable for single integral, and we will integrate n with respect to y. So that's why now there is no need to put any further dot dr or anything else. And you can see that a dot dr actually gives us m dx plus n dy, and this dx and dy, they actually perform the role of that single integration that we need for line integrals. And the right hand side remains the same. We have to write the normal component, but now instead of n cap we can write down k cap, because now we are sure of the direction. Usually in general we represent the surface integral via n cap, because we are not sure of what particular plane we are talking of. But here, as we know that we are talking of xy plane, we have considered the xy plane. You can write this down here. This is the xy plane. So if we have to go for any unit vector like n cap, so that would be k cap, because that would point in the z direction. So now instead of n cap we can write down k cap, because now we are sure of the directions and whatever plane we are talking of. Now what we have to do is that we know how to write down this del cross A. To solve a curl, we use this determinant, and since this is a cross product and that is order specific, order really matters. So if del is coming first, I'm going to write down the components of del operator first. Now just remember that for curl we include all the three directions. Even if we are talking of plane, for the determinant we will mention all the three directions, and then we can put the component of third direction as 0. So here this A is having x component, which is m. It is having y component, which is n, but it is having no z component, since we are talking of plane. We are talking of the vector function over the plane. So that's why this z component is 0. Okay, so this being the reason, but now we can expand it. We know how to do that. I cap would be this minus this. This is what we have obtained, then plus j cap, or if I have to write down this minus j cap, if minus j cap I'm using, then this would be this minus this, and then gets the k cap, which is this minus this. Here we go, here we have obtained the expression, and now we can write this down as minus iota, or sorry, I cap. Basically we use iota also in complex numbers, so this is but I cap, and this is plus j cap curly m by curly z, and this is plus k cap curly n by curly x minus curly m by curly y. Okay, so we have found the value for del cross A. Now you can see here we have this del cross A, which is having dot product with k cap and then ds. Now we have to find the value of this dot product. Let's do that. So if we have to write down this dot product, that means this whole expression would be having dot product with k cap ds. You know about dot product, only the same components interact with each other. Here we have only and only the k cap. It will not interact with I cap, because we know that I cap dot k cap is 0. We also know that j cap dot k cap is also 0. only k cap dot k cap is 1. So this k cap will only interact with this term and rest of the terms would give us 0. This implies this del cross A dot k cap ds would give us only curly n by curly x minus curly m by curly y, and ds is also there. Don't forget to put this ds. Most of the students, they just simply write it down and they forget about ds. They said that they feel that this k cap has performed its function and that's it. Only this is the magnitude and they forget putting ds. But see, physics goes step by step. It is so systematic. The derivation that we perform, they are so systematic and we follow one step after the other just naturally. We don't leave things just out of the blue. We don't bring out something out of it or just leave anything. No, whatever is there will go on until or unless we put some condition. So this is the expression that we have obtained, and now let's mark this equation as equation number 3. This is our equation 3rd, and this final expression that we have found, this is our equation 4. Now if we substitute the value from this equation 4 into equation 3, which is simply substituting the value for del cross A dot k cap ds, what we would obtain? We would obtain finally m dx plus n dy, and that would be equals to curly n by curly x minus curly m by curly y ds. Okay, so this is the expression. Now as the surface that we have considered was in xy plane, so we can write down ds as dx dy because it represents the xy plane, and thus what we obtain is m dx plus n dy integrated over the closed curve C, and that is equal to curly n by curly x minus curly m by curly y integrated over the surface S with dx and dy as the components or the variable with respect to which the integration has to be carried out. And this is Green's theorem in a plane. Here we have obtained our final expression, the Green's theorem in a plane. And you can see here we have the line integral which is being related to surface integral, and we have confined ourselves to xy plane only. You are not saying any z plane because this is the theorem only for a plane. Well, we can change this xy plane, we can replace it with yz or zx, but still the theorem will work only for the plane. We have one more form of Green's theorem which allow us to use two scalar functions. So we can understand that theorem as well, which is also known as modified, or some call it modified Green's theorem, some call it another form of Green's theorem, or some even state it as Green's theorem. So whenever asked to solve the Green's theorem, you can use either of these two versions. Either you can solve for Green's theorem in a plane, or you can solve the Green's theorem which involve two scalar functions. But in most of the cases, people prefer Green's theorem to be the Green's theorem in the plane that we have just discussed, because this is how it is famous. It is famous for it being the special case of Stokes theorem, and which we can only indicate or write down by showing the Green's theorem in the plane. But let's discuss the another form of Green's theorem. The statement of another form of Green's theorem goes like this: if phi and psi are two scalar functions, you know the most important way or the most common way to represent scalar function is by phi. But since we are having two scalar functions, so phi and psi, these are the Greek letters that we often use to represent scalar functions. So if they are having second order partial derivatives, then this is the expression. You can see phi del square psi minus psi del square phi, its volume integral is equal to surface integral of phi del psi minus psi del phi. Now, can you tell me what does this represent and what does this represent? Well, this is simple del operator and this is a Laplacian operator. Yes, you get it right. This is Laplacian operator and this is del operator. And del operator is acting on psi and there is no symbol in between. That means what does this represent? This represents gradient. And this is the Laplacian operator and it definitely acts on just scalar function directly. So here we have del operator and Laplacian operator, and on the right hand side we are having gradient of the scalar functions. And as you know that gradient can only be found of scalar function, and that's the reason that if you have taken scalar function, that remember that we can neither have divergence of those functions nor we can have curl of those functions. Why? Because divergence and curl can only be found of vector functions. And if you have scalar function, then the only possibility left is gradient. That's the only thing that we can do with the scalar function. That's why, since we are having scalar functions here, so the only function or formula that we can use is gradient. So that's what we have used here. And on the left hand side, we have the Laplacian operator. One more thing you can notice here is that here we are having this triple integral which represents the volume integral, and on the right hand side we have the double integral which represents surface integral. So this equation is relating volume integral with the surface integral. So the duty of Green's theorem is actually to relate two integrals, and we know that surface integral is the one, it's the main one. It actually, it depends on the way you are using it, that sometimes it relates with volume integral and sometimes it is related with line integral. So that's the common one. But we know that either we can have line integral associated with surface integral, or we can have surface integral associated with volume integral. We can never have line integral associated with volume integral. That is simply not possible. If you are simply drawing a curve and you expect a volume out of it, then this is meaningless. And there is no place for meaningless terms in physics. Thus, this form of Green's theorem is relating volume integral with the surface integral. Whereas the earlier form that we did, Green's theorem in the plane, that was relating line integral around the curve with the surface integral over the surface which is bounded by the curve. Whereas here we have the two functions. There also we had two functions, mxy and nxy we were having. Here we have phi and psi being the two scalar functions. But here we are relating volume integral of the fields, of the scalar fields that are present with the surface integral. So surface S is enclosing volume V. Can you decide that which theorem we would use in the proof? Like in the earlier part, we used Stokes' theorem since the statement was relating line integral with the surface integral, and we know that this is what we know about the Stokes' theorem. Stokes' theorem is the one which relates line integral to the surface integral, and that's why in the proof we used Stokes' theorem. And here we are having volume integral and surface integral. So can you think of a theorem which actually relates volume integral to the surface integral? Yes, we have a theorem which is Gauss divergence theorem. So you get me right that here in the proof we would use Gauss divergence theorem to solve. So Green's theorem has both the forms. You can perform either of the proofs in the exam if asked. One of the proofs deals with Stokes theorem and it relates line with surface integral, and the other form deals with Gauss divergence theorem and it relates volume integral to the surface integral. So let's start with the proof. It's the simplest one. It is simpler than the first form that we have done. This is far more simpler and the easy one. You can perform either of the two. As you already know that in the proof we are going to use Gauss divergence theorem, but still we know how to find divergence of a single vector function, or we know how to find the curl of a single vector function, and that was the reason that in the earlier form we used a vector A, which was used and which was further split into components, because we know how to find curl of a vector. Similarly, we know how to find divergence of a vector. So even if here the statement says that we are having two scalar functions, but we cannot find divergence of a scalar function. That is not possible. And Gauss divergence theorem involves divergence. We have to consider a vector. So to start, let's consider a vector, but we have the freedom that we can choose the vector to be of any type. So here we are choosing a vector which is made up of these scalar functions. Let's have a look. The vector A looks like phi del psi. We know only we can have gradient of scalar function, and gradient of scalar function is a vector quantity. So we can easily relate any gradient of scalar function to a vector. Here you know that this is scalar and this is also scalar. When del operates on the psi, which is a gradient, this comes out to be vector. It's a vector. And when a scalar acts on a vector, again we get a vector. So thus, it is totally justified to write down vector A as phi del psi, because the right hand side also comes out to be a vector. Okay, so whenever we can define our vector field to be like anything, but we have to keep the norms in mind. The norms say that right hand side should be equal to left hand side. So if you are taking a vector on left hand side, your right hand side should look like a vector. Even if it involves scalar, you have to use those formulae or terms which make a vector out of them. Since this form of theorem involves volume and surface integral, so we have to use Gauss divergence theorem, which states that the volume integral of divergence of vector function A is equal to surface integral of the vector function A. And remember this A dot ds, this involves n cap ds. Always remember. See, whenever we talk of surface, this particular thing should be in your mind, that n cap is there. We have done this many times. Again, we have to write down what would be del dot A. I'm going to write down directly. You can still solve and find whether do we obtain this expression or not. It's a dot product between del operator and vector A. So it's going to be a scalar quantity. And here we have the scalar quantity. We have marked our equations 1 and 2. If our vector A is phi del psi, let's write down how would it look like. Phi is a scalar function, just keep it as it is. And now for this del is operating on psi and it is basically the gradient of psi. First I'm going to write down iota curly by curly x plus. Again, sorry, I always call I cap as iota, but just remember it is I cap. And now this is operating on psi. Del operator is a vector operator. It is operating on scalar function. So we would obtain a vector. Here I'm keeping this phi as it is. And this gives us iota curly psi by curly x, because we know that this del operator itself has no meaning. It waits for something to act on. And now it will operate on psi. So psi will get settled here. So by this we get this expression. And now this phi is scalar, and we have just simply put it in front, and there is no symbol in between, so no dot product, no cross product. So we would say that it will simply get multiplied just like any number. If we had 3 here, 3 would have simply multiplied with all the terms. Same goes for phi. I can write this phi curly psi by curly x and I cap plus phi curly psi by curly y j cap and phi curly psi by curly z k cap. This is the vector A. But we have to find del dot A. You can see we are using Gauss divergence theorem and it involves del dot A. We have to find the divergence of A. We know what is our A. Now let's find divergence. So divergence del dot A, again del operator would be having dot product with vector A. But we have just written that how this del dot A would look like. So first just write this down. This is curly AX by curly X plus curly AY by curly Y plus curly AZ by curly Z. As we know, generally we express our vector as AX I cap plus AY j cap plus AZ k cap. So anything which is with I cap is the x component of the vector, something which is with j cap is the y component, and something which is with the k cap is the z component of the vector. Now here in this expression, whatever is with I cap, that means this is AX. This portion is AY, the y component of vector A, and this is AZ, z component of vector A. And here this del dot A says that now we have to find partial differentiation of x component of vector A with respect to x. Then we have to add that to the partial differentiation of vector A's y component with respect to y, and then we will add that too with the third term, which is obtained by taking partial differentiation of z component of vector A with respect to z. Now we know what is AX, AY and AZ. So let's substitute. So this becomes curly by curly x of phi curly psi by curly x plus curly by curly y of phi curly psi by curly y plus curly by curly z of phi curly psi by curly z. Now this is partial differentiation. It is acting on two terms. We would use product rule, which is there in differentiation. So using product rule, I just mark it here. What do we get? First, this curly by curly x would operate on phi, curly psi by curly x would remain as it is, and in the next step, curly by curly x would operate on curly psi by curly x, leaving phi as it is. Okay, so one time it will operate on one function. Let's do this. First time operating this on phi, we get curly phi by curly x and curly psi by curly x as it is, plus phi as it is, and this would operate on this. Since curly x is there in the denominator here and here as well, so this would give us curly square psi by curly x square. Then comes the second term. First we would be having, so it's like this. First this would operate on phi. We have curly phi by curly y and curly psi by curly y as it is. And in the next step, this would operate on this thing. So phi as it is. And since curly y is there in the denominator, so this gives us curly square psi by curly y square. Then the next term, this would operate once on phi, which gives us curly phi by curly z and curly psi by curly z as it is, plus in the next term it would operate on this, which would give us phi as it is and curly square psi by curly z square, since we have curly z here and curly z here as well. Now let's see how we can write this down. First, let's arrange the similar looking terms. Here we go. And now let's see. Here you can see that phi is common to all these three terms, and we are having second order partial derivative here. Does it look like something? Have we seen this expression before? Well, yes, this is Laplacian operator, the del square. We have our Laplacian operator del square as this, and you can see here we are having curly square by curly x square, curly square by curly y square, and curly square by curly z square. And we know that psi is a scalar function. So basically this Laplacian operator is operating on psi. So we can obtain from here that this is phi with del square psi, this complete term. And for these, what we can write? See, out of these three terms, one of the term is having differentiation with respect to x of phi and another is having of psi with respect to x. Then again, differentiation of phi with respect to y, then psi with respect to y. Then again, differentiation of phi with respect to z and that of psi with respect to z. It is single order derivative, partial derivative. That means, and since the function is scalar, so we can only think of just one thing which is happening over here, and that is gradient. Yes, del operator can act on a scalar function only in the sense of gradient. When we have to find the gradient, that is the only way possible to deal with scalar functions. So that means here we have this whole quantity is nothing but del phi dot del psi. Let's see, is it true or not? If we have del phi, that means this del operator is going to act on the scalar function. And we know that when del operator acts on scalar function, ultimately we obtain a vector quantity, which is like this. Similarly, we can write down for psi. This also looks like almost similar to what we have written for phi. Here this del operator is acting on psi, and again we would obtain a vector quantity. Since both are vector quantities, if we take dot product between them, then what would happen? I cap will only interact with I cap, j cap will only interact with j cap, and k cap will only interact with k cap. So here we have this our del phi, and it is having dot product with del psi. And what we would get? Only a scalar quantity. Thus, this is the expression that we have obtained if we take dot product of del phi with del psi. And this is just similar to what we have here. So that means this whole expression is phi del square psi plus del phi dot del psi. Here we have del dot A, which is phi del square psi plus del phi dot del psi. Now what do we have to do is that we have to substitute this value in the value of del dot A, which was there in equation 2. So you can see here the equation 2, and we have del dot A here. Now the value that we have obtained for del dot A, we have to substitute that value here. Let's do that. As you know, we have del dot A dv in volume integral, and that is equal to the surface integral of A dot ds. This is our equation 2, and we have substituted the value of del dot A like this. Now you can see we have substituted the value of del dot A which we obtained in equation 3rd, and on the right hand side also we have the value of A. This was our A. See here, we said that we assumed that vector A is phi del psi. So same value we have substituted in our equation on the right hand side. This is what we obtained. Now we can write A as psi del phi also. Since A was written as phi del psi in this, you can see here, originally we took A to be phi del psi. And we know A is a vector, and the right hand side is also a vector, the right hand side of equation 1. When del operator acts on any scalar function, this is basically a gradient, because when del operates on a scalar quantity, then that expression becomes gradient. We cannot have divergence of scalar quantity, we cannot have the curl of a scalar function. We can only have divergence of vector function and curl too of a vector function. And also gradient of only scalar function is possible. So here when we take gradient of scalar function psi, we obtain a vector, and then again we have another scalar quantity phi. So phi multiplied by any vector would again give us a vector. You know, scalar multiplied by a vector gives us a vector. So if we have written A here as phi del psi, we can also write it down as psi del phi. The things would remain the same. Again, A would still be a vector, and we still are using the scalar quantities psi and phi. We have just interchanged their position, because ultimately possibility is we have both the functions, we have both the scalar function phi and psi, and we can have gradient of psi, or we can have gradient of phi. So that really doesn't make any big difference, because here if we take del of phi, again we would obtain a vector, and then psi is a scalar, and scalar multiplied by vector would again give us a vector. And since psi and phi are scalar quantities, so even if we interchange their position, that won't lead to any significant difference. But since we took here phi del psi, some people might think that why phi is coming first and why psi is coming next, why we have taken gradient of psi and not phi. So to counter that why question which arises in many viewers, we have done this step, that let's write down A again as psi del phi, because we don't have any powerful reason not to write it like this way. So we are going to write it both way, because both way are possible. So in that case, all we need to do is whatever final expression we have obtained for del dot A, we have to interchange phi and psi. So this del dot A expression which is our equation third, we have obtained for phi del psi. If we obtain this expression again, this divergence of A again, by using A as psi del phi, then things would almost remain the same. Only difference would be that psi would come at phi's place and phi would come at psi's place. Let's do that and see what do we get. Now here, the equation 5, you can see we have written del dot A by assuming A to be psi del phi. All we have done is that we have interchanged phi and psi. That's it. Everything is same. See, in case of phi, we are writing psi. Then del square comes, and then instead of psi in equation third, we have written phi in equation 5 plus del phi dot del psi. In here we have written del psi dot del phi because this is a dot product and dot product is commutative, so it will not lead to any difference. We can write it either way. Again, we can use equation 2 and equation 5 and we can substitute the value of equation 5 in equation 2. Once again, this is our equation 2, which is Gauss divergence theorem, the statement of Gauss divergence theorem. So we have del dot A dV, which is equal to A dot ds. Now by assuming A as psi del phi, we have obtained the expression of del dot A, which is our equation 5. And we are substituting this value of del dot A from equation 5 into equation 2. And our equation 2 becomes psi del square phi plus del psi dot del phi dV and triple integral, and then surface integral of psi del phi, which is the new assumed value of A. Now next step is to subtract equation 6 from equation 4. We have obtained equation 4, which was due to A as phi del psi, and then equation 6 is obtained by assuming A as psi del phi, and we are subtracting equation 6 from equation 4. Now what would happen if we do that? First we would just write down what is our equation 4 and then we'll subtract equation 6 from it. So the left hand side of equation 4 is what? It's phi del square psi plus del phi dot del psi that we have written, and then minus sign, and then we would write the left hand side of equation 6, which is psi del square phi plus del psi dot del phi. Okay, and then we have written them in bracket first. This is dv, and then we have to write the right hand side, which would be double integral of the values. So first we would write the right hand side term of equation 4, which is phi del psi, and then we would subtract the right hand side term of equation 6, which is psi del phi from it, and then we have this dot, and then this is ds. Now one thing you can see here is that we have obtained this del phi dot del psi, and here we have del psi dot del phi. This is a dot product, and we know dot product is commutative. So A dot B is B dot A. That means the answer, the scalar answer, which we will obtain by having dot product between del phi and del psi, like if we write del phi first and then del psi next, or if we write del psi first and then del phi next and take the dot product between them, the answer obtained would be the same. And remember, we have this negative sign here, so these two quantities will cancel each other, and rest, whatever is left, is our Green's theorem, the another form of Green's theorem. Here you can see, so the ultimate expression is phi del square psi minus psi del square phi dv, and the triple integral of that, and then we have the surface integral of phi del psi minus psi del phi. Let me correct here, that was written by mistake. This is psi del phi dot ds. So this is the final expression, which is another form of Green's theorem. So here in this video we did Green's theorem and two forms of it. First was Green's theorem, which is also known as Green's theorem in the plane, and it relates line integral with the surface integral. And the another form that we did was relating the volume integral with the surface integral. Both have their own importance. If in exam you are asked to do Green's theorem in a plane, then you have to perform the first one. Then this particular theorem that we did, which is relating line integral with the surface integral, this theorem you have to attempt. But if you are just asked that do Green's theorem or derive Green's theorem, then you can choose either of these two versions. And now you know that Green's theorem has two versions or two types. One relates line integral with the surface integral, and the other one relates volume integral with the surface integral. That was all for today, and with this we conclude our video lecture series based on the topic vector analysis. I hope my videos would help you to understand this topic better. And if you have any queries, please mention them in the comment box below, and I would really love to answer those queries. That's all for today. Now we'll start with another series, and you will see a lot of videos dedicated to physics from the topics of undergraduate courses or postgraduate courses, and even you can ask me to make video on any particular topic. Thank you.